This video is about identifying domain and range of a situation table or function rule and determine if what an ordered pair means and if it is realistic. So let's practice identifying the domain and range of a problem situation and table below and then determine if a point is realistic. So Emily pays $23 every time she goes to get a manicure. So our function rule, if we have C for cost and M for manicures, cost is equal to $23 per manicure. So if she gets 0 manicures, she has spent $0. If she gets 2 manicures, 23 times 2 gets us $46. If she gets 4 manicures, 26 times 4 is 92. And if she gets 6 manicures, this is $138. So when we look at domain and range, we don't always just want to pay attention to the X. We need to use a little common sense. Can she get an odd number of manicures? Yes, because every time you're increasing your manicure by 1. So our domain here would be 0, 1, 2, 3, all the way to n, which remember another way we could say this then is it's the integers, because we're not using any decimals, greater than or equal to 0. The range is how much our cost is increasing by. So first we start with a cost of 0. If she was to get 1 manicure, it'd be $23. 2 manicures, $46. 3 manicures, $69. And we can continue this pattern for 23 times n. So is the point 9207 realistic? So we have to ask ourselves 2 questions. First, can she get 9 manicures? Yeah, she can get 9 manicures. That's a realistic thing. Will it cost $207? So we need to do our scratch work. 9 times 23, which gets us 207. So is it a realistic point? Yes, because it is a solution to the function rule. Number 2, roses cost 30 cents per rose plus a delivery of $5. So we're going to let C equal cost and R equal roses. So cost is equal to 0.30R plus $5. So if you order 1 rose and we're going to have it delivered, we have 0.3 times 1 plus 5 gets us $5.30. 3 roses times 0.3 plus $5 gets us $5.90. 4 roses, 0.3 times 4 is $6.20. And 5 roses would cost $6.50 using our function rule. So for domain, think about this. We are delivering. So can I order 0 roses to be delivered? No, they're not going to deliver me anything. So my domain can only start with where they would start delivering things, which in this case is 1. So we have 1, 2, 3, so on and so on to n, which means this would be integers greater than or equal to 1. Our range is what our lowest cost starts at, which for 1 rose is $5.30, for 2 roses $5.60, 3 roses $5.90, and that would continue with the pattern that follows our function rule, 0.30R plus 5. So is 15 a realistic point? So can I order 50 roses? Yes, that's realistic. Does it work in my cost equation? So 0.30 times 50 roses plus my $5 delivery charge. When I solve that, I get a cost of $20. So is this a realistic point? No, because the y coordinate would be wrong for the function rule. So we would say no because it is not a solution to the function rule. Number 3, the car you are traveling in is traveling at 50 miles per hour. So the function rule, we have distance for how far we're going and hours in the car. So distance is equal to driving 50 miles an hour times the number of hours we're in the car. So if we're going for 0 hours, we haven't gone anywhere yet. We haven't left, so our distance is 0. If we have gone 1 hour, we've gone 50 miles. If we've driven 2 hours, we've gone 100 miles. And if we've driven 3 hours, we've gone 150 miles. So our domain here, we need to think about hours. Now, all of our tables going up by 1. But do I always drive for a set number of whole hours? No, think about your ride to school. It might only take you 20 or 30 minutes. That's not a whole hour. So our domain here can include fractions and decimals. It can't include negatives, but it can include fractions and decimals. So we're going to say all real numbers. We have to be careful here and say greater than 0 because we can't have any negatives involved for our hours. So what is our range? Well, now because we have a domain of all real numbers, we need to consider, can our range be all real numbers? Well, if I'm multiplying 50 miles an hour times fractions and decimals, I'm going to get fractions and decimals out sometimes. So our range is also going to be all real numbers greater than or equal to 0. So is 0.24120 a realistic point? So I'm going to multiply 2.4 times 50 miles, and I get 120. So is this a realistic point? Yes, because it is a solution to the function rule. Number 4, Julia is babysitting and earns $11 an hour. So P is going to be payment and H is going to be hours. So P equals 11H because she's making $11 per hour. So if she babysits 0 hours, she makes $0. If she babysits 2 hours, 2 times 11 is $22. If she babysits 3 hours, 3 times 11 is $33. If she babysits 6 hours, 6 times 11 is $66. So again, we have to think about our domain. Be careful, we're with hours again. So when you babysit, are you always watching them for exactly that number of hours? No, you might be 2.5 hours or 2 hours and 15 minutes or 45 minutes. So the domain here again is all real numbers greater than or equal to 0 because you can have fractions and decimals of hours. Our range here follows the same idea. All real numbers greater than or equal to 0. So is 15,175 a realistic point? Well, if she's babysitting 15 hours times $11, that's only $165. So it is a realistic point? No, because it is not a solution to the function rule. So use the graph to the right to answer questions. So now we're going to analyze our graph to answer some few questions. So at 50 seconds, who's winning the race? So we're looking at the graph, we have 3 runners. Jamie is the solid red line, Chris is the dotted green line, and Brad is the dotted blue line. So if I look at 50 seconds, remember to win a race, you need to be going the furthest distance. So I want to see who's the highest up on the distance. Well, Chris has the highest y coordinate, which means that Chris would be winning the race at 50 seconds because he has gone the highest distance because Chris is right here and the other 2 are below him. Number 6, according to the graph, what happens at 75 seconds into the race? So on my x coordinates, I'm going to look at 75. And at 75 seconds, this blue line and green line are overlapping. And when something's overlapping in a race, that means they're at the same distance, which means it's a tie. So what's happening? We would say that Brad and Chris are tied. Who wins the race? So to win the race, you have to get to the distance of 600 meters, which they all got to in the shortest amount of time. So the first point to get to 600 is this red line in the shortest time, because blue and green are finishing in later times. So the winner of the race would be the red line, which is Jamie. So Jamie would win the race. Approximately what time did each runner finish the race? So we need to look at our three lines. So the yellow line for Jamie, notice that the solid tick mark is going up by 25 seconds. So she's higher than 75 and kind of close to 100. So we're going to say about 90 seconds. For Brad, the blue line, it's a little bit over 100 but kind of close. So we're going to say that's going to be about 110. And Jamie finishes, and Chris finishes right at 125 seconds. So approximately what time did each runner finish? So Jamie was about 90 seconds. Brad was about 110 seconds. And Chris was about 125 seconds. Number 9, a banquet hall has the following configuration around a table. Place X where each person sits. At a party, 4 tables are pushed together as seen in the picture to the right. How many people can sit at the table configuration now? So on the sides that are skinny of each table, we can fit one person. So 1, 2, 3, 4. We don't want any people in the middle here because this would mean that they're sitting on top of the tables. On the longer sides, we can fit 3 people. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. I wouldn't want people again in the middle here because then they're going to end up sitting on the table because the tables are pushed together. So now I just want to count my X's and figure out how many people would fit at the table. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So they could fit 16 people at the table configuration.